Rhino 8 is known as a powerful 3D modeling software, but you can supercharge its capabilities and customization through its code editor. I'll be going through the basics in this video with some demonstrations. Scripting in Rhino in itself is nothing new, with the ability to code using Python and C# in previous versions. But what is new is the ability to use cPython. This may not seem like a big deal, however, what this does allow you to do is take advantage of the full potential of Rhino scripting through its vast, publicly available Python libraries directly. This course is focused on using Python in Rhino, so some basic Python understanding will be useful, but I will be going through basic geometric examples, so both beginners and intermediate users can follow along. Jumping into Rhino, the script editor lives within Grasshopper, which is a visual programming language and environment that runs within Rhino. So you can type Grasshopper in the search bar to open it up. If you click in the canvas and type script, you see all the languages you can script with. But this bottom one can change the languages from one single node. Simply press the 3 dots and you can switch between other languages. C# is a faster language, but can be more difficult to learn, and Python is the same as cPython with a few core differences, with one big one being that you cannot use external Python packages. So I'll be using cPython, which is added here by default, as you can see by the logo. When you double-click this node, it brings up the script editor. In here you can write all your functions, which can use input data from Rhino or Grasshopper and output however you like. I'll close this, and you can still see that this looks like a typical Grasshopper node. You can insert any geometrical or numerical input at the start, and whatever is output, you can connect to the rest of your Grasshopper script. Very useful. For example, I'll add 2 number sliders here and connect them up to the X and the Y. Double-click to open the node, delete the default text, and we can access this input value by simply typing the names. Here X is set to 3. Confirm that this is working in the script editor. I can write print, and within the parenthesis, enter X. If I run this in a terminal, below you will see the value 3. This value is only stored internally, so if you want to output, we have to write A equals X. Our output variable is here called A, but you can right-click and rename it to anything you like. I will add a panel and attach it to A, so that you can see the value 3 output now. If you change the slider, it will update this output. This in itself isn't very useful, but I want to demonstrate to you the flow of data, which is very important and a basic step, as next we'll be creating functions to use these inputs. Now Rhino will be nothing without its powerful geometry library. If I go on to showing external Python packages, you'll want to learn what you could do programmatically with Rhino. As you can imagine, this library is massive. However, there's help at hand. If you go to the help in the toolbar and find Show Rhino 7 libraries, you'll find references to all these. It says Rhino 7, as you can see there are also Rhino 8 libraries. The 2 main ones you want are RhinoScript syntax and RhinoCommon. RhinoScript is easier for beginners, more high level and suitable for simpler tasks, while RhinoCommon is more powerful and flexible, as it is .NET based and suitable for advanced tasks and plugin development. For this reason, I would recommend going with RhinoCommon for most of the tasks. So let's look at this library. They are organized into various namespaces, each containing classes and methods for specific functionalities. Key namespace here is Rhino Geometry, and as the name suggests, contains classes and methods for working with geometric objects. These include all the family classes such as points, curves, b-reps, and so forth. But to access all these, we need to import it, which simply can be done by typing in import and rhino.geometry as RG. As you can see, the Rhino 8 Python editor has a much better autocomplete as well. And the RG is an alias, which makes it easier to reference this library, which you'll see later. Now let's make some geometry from the inputs. Point3D is a great place to start. I will scroll down to find this and expand. You'll find constructors here, which show you what is needed to create this Point3D and what parameters. You can right-click and also open the help in the browser. This takes you to a very useful page, which has all the same RhinoCommon documentation, which you will need to experiment with different geometries and classes. It is much clearer here to see and understand. You can see that to make a point 3D, you need to input an X, Y, and Z as a coordinate. So let's go back to Grasshopper. And we already have an X and a Y, so let's add a Z. When you zoom in close to the node, you'll see this plus icon to add extra inputs. So let's click on this and add another variable. You can right click and rename this, but Z is actually what we need. I'll copy this and connect another slider. Now for some additional info about these inputs. If you right click them, here at the bottom, you can change them from a single input to a list or to a tree access, which is a more advanced way to handle data in Grasshopper. Although item and list will be the main ones you need. You can also go to the hint types and change the variables to specific type or class. Here I will explicitly select the int. This is not always necessary. As you can see, it works in other sliders without me changing input details. But it is good practice to be explicit in the inputs, as it can prevent errors down the line when only certain data types can be used as inputs. While we are here, we can rename the output to points, as that's what we want to generate. Now with input and output variables sorted back in a script editor, we can write our first geometry class. Type RG to reference the rhino.geometry library, then add a dot followed by the point3d and some parentheses. You can see the autocomplete coming up, prompting 3 coordinates, so let's reference our X, Y, and Z inputs. As simple as that. Now we can save this to our output by placing the point equals here. Then you can press run. A generic error has come up, but has nothing to do with the code, so we just have to run it again. Now if I head over to the point output, you can see there is a point geometry created, and in addition, you can see the point coordinates in the panel here. And of course, we can confirm this by going into the Rhino 3D view. As we change the sliders, the point will change based on the relative X, Y, and Z coordinates. From here, you can save the output into an actual Grasshopper point node, and then use it in the rest of your Grasshopper definition. For completion, you can right-click the actual script editor and rename it to something more meaningful. And with that, you've created your first Grasshopper component with the cPython script editor. Now that we have the basics covered, we can step up by adding more classes based on this point and then importing an external Python library, which wasn't possible in Rhino 7. I'll copy this component. Now I'll make a simple building massing from this origin point. I'll add 3 more inputs for length, width, and height. I'll go through this time and change each of these to integers, although it could be a float, which is a decimal value. I'll create 3 sliders and plug each of these in. And then our output will be a box, which can be saved as a BREP. Let's double-click the script editor and take a look at how we can make a box from this point. Same as before, we can go to the Rhino library help, open up RhinoCommon, and have a scroll for the box class. Let's pick the first one, right-click and check the documentation. We can see here that a box can be defined first by a bounding box, which can be made from a collection of points, or down here you can see that just 2 corner points are also enough. With this understanding, we can just make 1 more corner point and we have the bounds of the box. You can find this same logic here on the bounding box. If you open up this constructor, you can see essentially 2 points each with an X, Y, and Z are needed to be defined. As you work more with the geometry libraries, you'll find that often geometries are built on top of other geometries. And so here you can see why the bounding box is required to make a box. So let's add our 2 corners. So we can save the first point to a variable called corner1, and then make another corner called corner2, and use the same rg.point3d constructor. Now to make the corner box for the upper bound, using our input, we just need a little bit of math. We'll take out my handy snipping tool to explain. So we have our Z, X and Y coordinates, making this point at the bottom bounds. We can take each of the length, width and height inputs and add them to each. So that when we add the length to the X, width to the Y, the length to the Z, together that will allow us to control the upper bounds point and make the box. So let's create this logic in our script. Create an rg.point3d. We can select the autocomplete option. Then for the parameters, type X plus length, Y plus width, and Z plus height. As long as these are spelled correctly to match the inputs, it will work correctly. You can confirm this visually by adding these points to outputs. So we could do A equals corner 1 and B equals corner 2. We don't have a B output, so we can add one here. Let's move over to our viewport. And we can move these sliders. You can see that the bounding points are also moving. These and make the actual bounding box needed to create the box geometry. Create a variable bounding box to save into. Then equals and use the rg.boundingBox constructor, as shown here in the documentation. Within the parenthesis, we can just add the two 3D points we've made, and then we can save these into the variable corner 1 and 2. The last step is then to add this to the box constructor. Add the variable box, which is our final output, and then the constructor rg.box. Within parenthesis, we can then add the bounding box we just created as per reference. I forgot to add equals at the start, so I'll do that. And to recap, what these two steps are doing are creating the points on the two corners we defined using the grasshopper sliders, and we use that bounds to create our box geometry. Now we can run the script. I have accidentally turned on the debug mode here. I won't go through that in this lesson, but lets you go step by step through the code. And you can see the variables output in the terminal below. So it's pretty useful when you get to more advanced scripts. But for now, I'll exit that and just hit run again. Now that has worked, you can see that the panel shows a closed brep and that the brep is no longer red. If we move to our viewport, you can see our volume. We can adjust our original position and all the dimensions. We can also tidy this up a bit by removing the A and B outputs as they're not needed. Of course, there are already components to make boxes in Grasshopper, but hopefully you'll now understand how you can combine various constructors and classes with customized inputs and outputs to create whatever you like. Working with geometry is great, but having the ability to work with data and other calculations is a must for many designers. This is where external libraries for handling this data can be useful. This is a good opportunity now to show you how to install and use external Python libraries. I'll disable this component and duplicate it. I'll be demonstrating this on a very popular Python library called numpy, which provides support for multi-dimensional arrays and matrices, along with a collection of mathematical functions, transformations. I will just rename this to numpy. If you would like to see what libraries are available, go to pypy.org, where you can find thousands of projects. If you follow through the links, it will bring you to all the documentation and usage. To install this in a script editor, there are two ways. The first is to type #r and then a colon, and then the name of the package. When you run this, the script will automatically install it once. As you can see, nothing has happened as I've already installed it. The second way is to press this icon at the top and simply type in the package name, which is numpy. You'll click install. Once installed, you can reference it here in the script editor as usual. So import numpy as np, with np being the shorthand alias. Here I'll use numpy to extract all the corners of our bounding box and make an array, which then could be used for other transformations or data analysis once it's structured. Get the corners. You can see in the documentation that there is a getCorners method. A method in programming is a function that is associated with an object or class. It is used by typing the class, which here is bounding box, and then .getCorners, which is the method. I will save this to a boxCorners variable and add this variable to the output of the component so we can visualize it. If you hover over this, you can see we have a list of lists, which creates a point. This is great for geometry, but not for data analysis. So let's convert this into a numpy array. I know the function is called np.array, and it can take our x, y, and z coordinates for each point to make it. I'll use a list comprehension for this. I'll type it out first and then explain. My autofill has been writing print instead of point, so we'll change that. And if you're beginning to Python, this might be a bit difficult to understand, but it is essentially a short piece of code that iterates over each point in the list of boxCorners. I'll add a boxCorners output, able to visualize the points. This will need 2 panels to see how the coordinate data is arranged. May also need to run the script again for this to update. So one panel is for the numpy array and one for the geometric point. The structure of the data is very different. You see that for the array, there's just one item for this, while in a point, it is just a list of geometric points. You ask what is the point of this array structure? And the answer is that now you have the ability to analyze and do mathematical calculations on this easy-to-use format. A simple example would be that I can find the mean of this coordinate array in one simple function, which finds the center point of the bounding box. I'll add a box center variable, and I know there's a function called np.mean, which finds the means of all the points. The parameters are simply that array that we made, and we just need to supply the axis. In NumPy, this means if an operation is performed along the columns or the rows. This is so that the average is calculated on all the x, y, and z values separately, and then combined. If you don't understand it, it's fine. It's just an example to demonstrate how to do analysis on geometry in Rhino. And if you're wondering how to find out about all the functions, how to use them, as expected, there's a comprehensive documentation online with all this. Now we have a center point. We can print it and check that the average point is created, which we can confirm in the terminal, as it gives us 3 coordinates. Now let's actually output the point. So I'll add another output component and call it box center. Since the output is a numpy array and not a 3D point, we need to restructure this one more time to take in each of the 3 values and convert them into the x, y, and z to create the point for Rhino. We will do this with a good old rg.point3d function. And I need to first access the first, second, and third value from the array, which is counted starting from 0 in computer science. So the expression will be box_center 0, access the first element of this array list, which represents the x coordinate of the center point. Similarly, use box center 1 and box center 2 in the square brackets to access the y and z coordinates respectively. This together creates our point. We can verify this in the viewpoint by changing our slider to see how it all dynamically updates. This may seem all quite complex, and you may say that simple boxes and center points can easily be done in Rhino already, and you'll be correct. If you go to the Help, Rhino libraries, we can scroll to the RhinoCommon library and find the bounding box already. Here in the properties, you'll find the center, so you could go and use rg_boundbox.center. However, this is a good learning exercise to show you how there are many solutions to the same problem and how you can fully customize the code to your needs, which you'll need to create more advanced solutions. The average is simply a function. If you read through the documentation, you can find far more complex functions, which you cannot do in RhinoCommon. These were the 3 main examples I want to take you through. Just before I end, I will show you one more complex example where you can use other geometric inputs, such as B-reps or curves in this instance. As we change the curve in Grasshopper, it dynamically updates with the script. This example was created using the same logic as the first two examples using RhinoCommon, but it just takes a curve and max input height and creates volumes based on the specific number of levels. I'm using here the Rhino geometry. It checks to make sure the input curve is closed, then calculates the floor height by dividing height by number of levels. You can always change this so that you can manually specify the floor height through a slider. Here is then a for loop to generate volumes for each level. It does it by duplicating the curves and translating them according to our inputs. And then using the extrusion function, it creates the floor levels as BREPs. You can find this function in the RhinoCommon documentation in Rhino geometry under extrusion. This list of BREPs are then added to the volumes list and output to BREP. So I've just scratched the surface here with the script editor. I'll provide all these examples as references, so feel free to explore and continue learning by developing your own solutions in the script editor.